The Media Lab has been researching holographic television since the groundbreaking work of the late Professor Steve Benton in the late 1980s, and my group has been participating in that work since the early 1990s. And we started off looking at the computational aspects. How do we compute holographic video in real time? And that's moved toward how do we compute holographic video in real time using consumer-grade technologies, PCs, set-top boxes, the kinds of graphics processors that we'd find in consumer products, because we want to do this inexpensively, and we want to ride the technological wave that's advancing the amount of computational capacity that consumer products are increasingly coming to have. Beyond that, we're also interested in building the displays, and to that end, we've built holographic video displays. We're now making very, very high capacity light modulator chips, where we're making a very inexpensive tens of dollars chip here on campus that has as many pixels as 1,000 video projector chips. We are also building end-to-end holographic television systems where we point a range-finding camera like a Microsoft Kinect at a scene. In one case, one of the graduate students dressed as Princess Leia, and we transmit that scene holographically across the internet to a display, and we create a complete end-to-end holographic telepresence system. We're also looking at human factors issues in holographic displays, so trying to understand what kinds of tasks, whether they're perceptual tasks or manipulation tasks, such as teleoperation, can be enhanced by a more realistic display, and one that provides more comfort and more perceptual accuracy. There are two big motivations for doing holographic television research, and one of them is the fact that it's attractive in a science fiction-y sense. People have been thinking about this for a very long time, and we're finally at a point technologically where we can build it. And for many people, that's sufficient motivation. But there are some very real advantages to having a holographic display. There has been a big attempt in recent years, both in the movies and in consumer electronics for the living room, to resurrect the notion of 3D movies and 3D television. And in that sort of 3D, the system provides a different view to the left eye and the right eye, and it, to some degree, gives a perception of a three-dimensional scene. But there are problems with doing that. That doesn't provide all of the cues to the 3D nature of a scene that reality provides. For one thing, it doesn't provide what's called motion parallax. If I'm watching a 3D movie and I move my head left or right, the viewpoint doesn't change. The second thing that it doesn't provide is that when I'm watching a 3D movie or a normal stereoscopic 3D television, my eyes are always focused on the screen. In reality, my eyes are refocusing at all different distances. A holographic video display provides all of the cues to reality, to the depth of reality, not just the limited cues that a 3D movie or 3D television screen provides. Now, this has several impacts on the viewer, and one of them is simply comfort. People report that whether it's for entertainment purposes or for scientific or industrial purposes, looking at a 3D video monitor for an extended period of time is uncomfortable. And that's in large part because of the mismatch among the visual cues that the monitor is providing. And a holographic television display won't have that problem. There's a second issue which is even more important, and that is that the mismatch of the perceptual cues reduces people's accuracy in their ability to perceive the relative locations of things in 3 space. So that means if I'm trying to do a surgical operation at a distance or control a robot at a distance or even just understand data by visualizing it in 3D, my ability to judge the three-dimensional arrangement of the scene on the display is limited if it's an ordinary 3D display. And so a holographic display provides very significant benefits, not just in terms of comfort, but also in terms of allowing people to perform tasks accurately using such a display. The holographic video displays clearly would be great for video games, and there are people who would love to watch Downton Abbey or the World Series on a holographic video display. But at the same time, electronic displays are increasingly important in how people interact with information and interact with things at a distance. And so if I am controlling a robot, if I am working with a visualization of information. So I have data coming in and I'm making a three-dimensional visualization of it. It's very important for me to be able to have a very, very accurate perception of the spatial arrangement of the scene in front of me, whether just because I'm looking at it or because I'm actually interacting, perhaps by robotic control, with the scene at a distance. And a holographic display provides significant advantages in accuracy and in comfort in order to perform those tasks. As of right now, we have presented a desktop monitor that costs a few $100s and provides a color image. The image it provides is only postcard sized, but that was proof of concept that we could construct something very inexpensively. What we're moving toward is trying to make a desktop monitor sized display next. And then beyond that, we're looking to make a display that's perhaps a meter diagonal, and that will take a few more years. And we're also trying to do this inexpensively, and we're trying to do it in a way that we can take advantage of communication networks, communication standards, and electronic components and software that already are being developed for other purposes, so that we don't have to invent everything. We can concentrate our scientific and engineering efforts on the parts of the system that nobody else is doing. There are several things about holographic video research. One of them is there just aren't that many places in the world where it's even being done. And MIT is a great place to do this kind of work because it involves human factors, cognitive science, it involves materials science, it involves electrical engineering, signal processing, computer science, computer graphics, mechanical engineering. And MIT is one of the few places in the world where it's easy to grab students who have experience in those disciplines and get them involved in a project. Each of them feels that she or he is contributing in a meaningful way to something that he or she has been hearing about in the movies for the past 20 years.